Hello? Okay. Guess we can slowly get started. So we were discussing RowHammer solutions from industry, and we concluded that we need to come up with better solutions. Even though industry proposed some solutions for RowHammer, we show that they are not secure exactly. And now we will talk about some RowHammer solution approaches. So the first approach is to create or design more robust DRAM chips and/or error-correcting codes. And as you can imagine, this is a challenging job, and it's not like easy to come up with such designs while maintaining the current advantages of DRAM. The second approach could be increasing the refresh rate to an extent such that fewer activations become possible in a refresh interval, meaning that an attacker cannot activate DRAM rows enough times to create bit flips, but it is also costly. And the third one is physical isolation. I guess we talked about it a bit. And you put isolation rows in between aggressor rows and victim rows such that you have enough space to guarantee that the aggressor row cannot affect the victim rows to induce some bit flips. And this again has some drawbacks because you lose some rows or you change the design of the DRAM. So there are different drawbacks. And the fourth one is reactive refresh, which we will talk about in detail in a second. We also refer it as the preventive refresh. What we do in this approach is to determine if a row is being activated many times or hammered, and preventively refresh victim rows so that they don't experience bit flips. And the last one is proactive throttling, meaning that the mitigation mechanism slows down the attacker workload such that it cannot activate some rows enough times to induce bit flips. And all of these approaches have different costs, power consumption, performance, or complexities, and there are different trade-offs here to consider. I will now talk about some of our solutions based on some approaches that we just saw. The first one will focus on proactive throttling. So this work is called BlockHammer, and it was published in HPCA 2021. And it followed the throttling approach. So RowHammer is a worsening DRAM reliability and security problem, but the problem that we are focusing on right now is that the state-of-the-art RowHammer mitigation mechanisms face some limitations supporting current and future commodity DRAM chips because of two main challenges. The first one is that they are not scalable with worsening RowHammer vulnerability because these mitigation mechanisms induce more and more performance overheads or area overheads while we see more decreased RowHammer thresholds. Okay, there is a slight issue, I think. Because these mitigation... Oh, you are seeing my slides. No, it's just maybe we can just stop sharing. Oh, it says it's paused. So a bit flip happened. It's good that some people joined us in the meantime so that they can catch the exciting new mitigations that we will talk about. So if everything is okay. Okay, so we were talking about BlockHammer and the definition of the problem that it focuses on. So we were talking about existing RowHammer mitigation mechanisms become prohibitively expensive when we have low RowHammer thresholds. And they are not also compatible with commodity DRAM chips because they rely on proprietary information that is not available for all DRAM chips that we have. This information focuses on the address mappings, and I will cover it in the next slide. And the key idea of BlockHammer is to selectively throttle memory accesses that may cause RowHammer bit flips. let's assume that an attacker hammers a row to induce bit flips in its nearby rows, and existing RowHammer defenses detect the attack, and then they try to mitigate it by refreshing the rows with these addresses that it predicts to be adjacent to the victim ones, to the aggressor ones, sorry. And what can happen is that the DRAM device could remap these rows to different physical locations so that the memory controller is not aware of the exact location of that row address, and then refreshes some random rows over there. And the attacker can still induce bit flips in the actual victim rows. So existing RowHammer mitigation mechanisms need to know these remappings, like which row corresponds to which physical location, so that it can accurately, preventively refresh the correct victim rows. And in contrast, BlockHammer does not need this information because it does not focus on the victim rows. It detects the RowHammer attack using area-efficient balloon filters that Giray described in the earlier session. And BlockHammer selectively throttles and accesses from within the memory controller, meaning that it slows down the attacker such that the victim rows don't experience bit flips. So it doesn't need to know which rows are being the victim here. So when we apply this, bit flips do not occur. And BlockHammer can optionally inform the system software about the attack because it detected an attack, right? And the system software can take different defenses, like high-level defenses, can stop the threat or so on. And so following this, BlockHammer is compatible with community DRAM chips, and it doesn't need information about the DRAM mappings, or it doesn't need to modify the DRAM chip itself. So the evaluations show that in terms of scalability with worsening RowHammer vulnerability, BlockHammer is competitive with the state-of-the-art mechanisms when there's no RowHammer attack currently happening in the system. And it has better performance and DRAM energy consumption when there's an attack actively hammering some rows. And we look at 4 mitigation approaches in terms of different properties that we would like our mitigation to have. The first one is comprehensive protection. Second, compatible with commodity DRAM chips, scalability with RowHammer vulnerability, and deterministic protection. And BlockHammer is the only solution that addresses 4 desirable properties at the same time. So there are more things in the paper. We just covered the basic idea, and you can, if you're interested, then you can check our paper and learn more about BlockHammer. And in summary, BlockHammer is the first work to practically enable throttling-based RowHammer mitigation. It is implemented in the memory controller. It doesn't need to change the DRAM chip, or it doesn't need to know about the address mappings. It doesn't need to identify victim rows, and it can prevent bit flips. And it is both scalable and compatible when you consider worsening RowHammer and community DRAM chips. And it is also open source, so you can check our GitHub repo for that. So BlockHammer was evaluated with the lowest RowHammer threshold of 1,000, and it was like a decent future RowHammer threshold at that time. And after that point, we actually observed much lower RowHammer thresholds, being, like some DRAM chips were vulnerable to an extent that we need to evaluate lower RowHammer thresholds for future systems. And when we look at those low RowHammer thresholds below 1,000, we see that benign workloads start to experience bit flips, even when they don't target, like creating an attack or something. And that means that we need to have better solutions because BlockHammer throttles those applications as well. And it starts to induce more performance overheads. Let's look at the solution approaches again, and we will now focus on the reactive refresh, preventive refresh approach. The first work that I'm going to talk about is Comet. It was published in HPCA this year, a couple of months ago. And I will start with first describing preventive refresh. So in theory, refreshing potential victim rows mitigates read disturbance bit flips. I said in theory because to do so, we need to first track DRAM row activation counts accurately to preventively refresh correct victim rows. And let's look at an overview of preventive refresh-based mitigation techniques. So the first solution that you can think of probably is that to allocate one activation counter per DRAM row. Here we are describing these counters in the memory controller, and they count whenever we have an activation to one of these DRAM rows that is available in the system. And since these counters are pretty accurate, they are incremented each time a row is activated. They preventively refresh victim rows when it's absolutely necessary, and therefore their performance and energy costs are very low. So they don't do unnecessary preventive refreshes. But in order to track all these DRAM rows pretty accurately, we need to allocate a lot of counters because we have many DRAM rows in our systems today. So the area cost is very high. And the second approach leverages the observation that an attacker can only hammer a subset of the DRAM rows that we have in the system. So they have a limited time window, and then they are activating some rows, and the number of aggressor rows are much less than the total number of rows that we have. And in this approach, we allocate one activation counter per aggressor row. And since these counters are still pretty accurate, they are tagged with row IDs, and when you see a tag match, you increment that counter. You do some algorithmic stuff to basically determine which rows are being activated a lot, and then you track them. And that tracking is still pretty accurate, and therefore their performance and energy costs are still low, the mitigations that uses this approach. But again, we have high area cost in this case also, because especially at low RowHammer thresholds, we can have a lot of aggressor rows. So it just increases, like the number of aggressor rows that you can hammer X amount of time increases a lot because X keeps decreasing. And since we need to store some tags for these counters to identify which counter belongs to which row, we implement these with content addressable memories, which is pretty expensive. And the third approach aims to lower these high area costs and allocates less than one counter per DRAM row. And to do so, it either uses shared counters that track multiple DRAM rows that behave similarly and reduce the number of counters that they have, or they introduce probabilistic refreshes again. And since the number of counters that we have is pretty low, the area cost is also low, but the mitigations that are based on this approach incur high performance and energy costs because they basically use the DRAM bandwidth for preventive actions instead of doing regular memory requests, right? Because these are not as accurate as possible, the counters, they induce more and more unnecessary refreshes. Yes, please.
You can't activate other nodes partially by the aggressor. That's your comment.
I'm not sure if I'm hearing correctly. Maybe we can give the microphone. Sorry.
When the aggressor is fully active,
Mm-hmm.
you can't have other victim, possible victim nodes being partially active.
Yes. Yeah, basically what we assume is that when we detect an aggressor row and refresh its victims, assuming that those victims are
which is why they have bandwidth consumption.
They can be accessed later, and then you would overlap some latencies probably if you're refreshing and then accessing them. But the bandwidth consumption comes from the preventive actions, meaning that I am doing a lot of unnecessary preventive refreshes, and it consumes a lot of bandwidth, such that I cannot access DRAM for my regular memory requests. Is that okay? And ideally, we would like to achieve low energy processor chip and DRAM area and performance overheads. And we looked into different mitigations that are considered state-of-the-art in terms of different metrics, and we saw that none of these mitigation techniques achieve all of them at once, and our goal is to prevent RowHammer bit flips with low area, performance, and energy overheads in highly RowHammer vulnerable DRAM-based systems. So our key observation is that we have two types of counters that we can use. The first one being hash-based counters that are low cost, and the second one is tag-based counters that are highly accurate. And I will explain how these work next. So let's say that we have these DRAM rows and we have a limited set of counters. Hash-based counters map these DRAM rows to counters using hash functions. And since we use hash functions, we don't need to store any tags. We can just implement them with low-cost memory primitives, and then we can aggregate many rows activation counts together to summarize them with this limited number of counters that we have, and which makes it low cost. But as you can see from this picture, probably, this means that since we have a limited set of counters, some rows share some counters, and this introduces some inaccuracies in the counting method. And tag-based counters are, they have the benefit in that context because each of these counters tracks only one row's activation count, and therefore they are highly accurate. So our key idea is to use low-cost and scalable hash-based counters to track most DRAM rows activations with low area overhead, and use highly accurate tag-based counters to track only a small set of DRAM rows to achieve low performance overhead. And let's look at a brief overview of Comet. It has two key structures. The first one is the counter table that maps each DRAM row to a group of low-cost hash-based counters as uniquely as possible by employing the count mitigation technique. And it triggers a preventive refresh to an aggressor row's victim rows when the aggressor's counter group reaches an activation threshold. And this way, it tracks DRAM row activations at low cost. And the second structure is the recent aggressor table that allocates highly accurate per DRAM row counters for only a small set of DRAM rows that are activated many times to reduce the performance penalties by increasing tracking accuracy. And I will just cover the high-level summary of how Comet operates and then leave the details for later discussion, or if you're interested, then you can check our paper. So when there's an activation row A, Comet first checks the counter table that implements the hash-based counters and gets an estimation based on the counter table. And at the same time, it checks the recent aggressor table that has tag-based counters and gets an estimation based on that table. And when there's a tag match in the recent aggressor table, since these counters are highly accurate, we use that as our estimation. And Comet compares this estimation to a preventive refresh threshold that is configured before and decides on preventive refreshing victim rows or not. And I will not cover these slides, but I put them here for your reference. There are some problems that we solved with these, and you can check them yourselves, or you can ask questions and I would be happy to answer. So there are more details in the paper about counter update policies, periodic counter reset mechanisms, eviction policies, or other details about the implementation. So let me cover the key results of Comet. So Comet prevents RowHammer bit flips with low area, performance, and energy overheads across many single-core and multi-core workloads compared to a system with no RowHammer mitigation. And it achieves better performance than low area cost mitigations, and it achieves better area efficiency than the most efficient, performance efficient mechanisms. And yes, and Comet is also open source, and you can check our GitHub repo from this link. Yes. Okay. So in conclusion, our goal was to prevent RowHammer bit flips with low area, performance, and energy overheads in highly RowHammer vulnerable DRAM-based systems. And our key idea was to use low-cost and scalable hash-based counters to accurately track DRAM rows. And Comet tracks most DRAM rows with these low-cost counters by employing the count mitigation technique to achieve a low area cost, and tracks only a small set of DRAM rows that are activated many times with highly accurate tag-based counters to reduce the performance penalties. And we show that Comet achieves a good trade-off between area, performance, and energy costs, incurring significantly less area overhead and outperforming the state-of-the-art mitigation techniques. So if you have questions about Comet, I can answer them, or yes, please.
Okay. Sorry, can you explain better what is the purpose of the accurate tag-based? Because I guess it's inclusive compared to the hash counters, right? So you increment both counters at the same time. So why do you need this additional table?
So I will go back to the detailed slides a bit. Yes. So here we see that basically the counter table counters can saturate at some point where you have like many activations that are counted, and then you send a preventive refresh. And since these counters are shared across many DRAM rows, you cannot reset them. So we do not reset them. And that means whenever I have an activation to an aggressor row that I already preventively refresh its victims, I again send it. And to cover that, we introduced tag-based counters, and we basically size it such that we'll cover a lot of aggressor rows and accurately track their activation counts after they are preventively refreshed, their victims are preventively refreshed. And since the tag-based counters are pretty accurate, we avoid any unnecessary preventive refreshes. Okay. Any more questions? No. Okay. So let's move on to the next work that I'm going to talk about, which is called Abacus, and it will be published in Using Security this year, I guess. At this point, it's a bit future, as it's August. And this paper also has a preventive refresh-based approach, and it looks at a similar problem. We are looking at ways to reduce the area cost of activation counters and, like tracking with counters. Yes. So the goal of this paper is, again, preventing RowHammer bit flips at low performance, energy, and area costs, especially at very low RowHammer thresholds. And the key observation that this work leverages is that many workloads access the same row ID in different DRAM banks at around the same time. And the key idea of this work is to use one hardware counter to track the activation counts of many rows with the same row ID across all DRAM banks. And this means that we are effectively implementing RowHammer mitigation with very small hardware storage because we have many DRAM banks. And the results show that basically this work also prevents RowHammer bit flips with low cost and also with low area cost as well. And okay, so we looked at different ways to count activations, and in this work, we want to answer the following question: is R an aggressor row? And if we follow the probabilistic approach, this means that we will have low chip area cost, meaning that like para, it doesn't need to store any metadata or anything, but it will increasingly send preventive refreshes at low RowHammer thresholds, and it will start causing a lot of trouble in terms of performance cost. And the second approach is that we can have many counters to accurately track these DRAM row activations. That means that we will not have unnecessary preventive refreshes, but we will have a lot of chip area cost. And how many counters are too many counters, right? So we are always saying that we implement a lot of counters, and we let's just quantify it. So if we allocate one counter per DRAM row, that means that for some DRAM modules out there, we will have this many storage overhead, and then we will have this per DRAM module. And we want to implement fewest possible number of counters. And Misregues is an algorithm that summarizes this pretty well. This is, again, the same approach that I talked about, like as the second approach that implements one activation counter per aggressor row. And it is pretty good at actually tracking a lot of rows for many RowHammer thresholds, but when we go lower and lower RowHammer thresholds, we see that its storage cost increases a lot. And the motivation behind this work is that there are many banks in a DRAM chip, and this means that we have a linearly increasing cost, and basically many workloads access the same row ID in different banks at around the same time. I will show some data on that. And we call these rows with the same ID across all banks sibling rows in this work. And the key idea is to use and share one hardware counter for all sibling rows that we have. And this effectively reduces the number of counters by a factor of the number of banks in the chip. Let's focus on this observation over there, and why is that we have many workloads accessing the same row ID in different banks at around the same time. So we look at a system and with like a lot of applications here, and we look at the number of sibling row activations that we see over the course of windows of 128 row activations. And we observe that workloads access the same row address in different DRAM banks at around the same time. This is due to two reasons. The first reason is that the address mappings that we use in today's systems, they usually distribute consecutive cache blocks to different DRAM banks to use the bank level parallelism. So this results in having like a lot of accesses to the same row IDs across different DRAM banks. And this is one of the address mappings that we might be using. So this is one of the reverse engineered address mappings if you look at some prior works that we cite in this paper. And as a result of this, we see that access pattern. And the second reason is that workloads tend to access cache blocks in close proximity at around the same time, which is only like if you have a regular access pattern, which is what you expect. And the key mechanism this work uses is that it tracks the maximum activation count of sibling rows using one counter. And this is an example. So we have the same row ID across different DRAM banks. And basically, we will use the worst case activation counter for all of them. Again, I will not go into detail of the whole mechanism, but in here, we have some row activation counters and some vectors to keep track of which DRAM banks activating which DRAM banks. In which DRAM banks we have the same row ID activated as many times. Okay, and in this work, we use this system configuration to evaluate it. Again, you can check these later. And the key results are that Abacus prevents bit flips with low area overhead while maintaining low performance and DRAM energy overheads. And it outperforms prior mitigation techniques when you look at area and performance overheads. And there are more details in the paper that you can check from this link. And also you can check the source code from here. Okay, if you have any questions, I can take them. No questions. So we covered a lot of works focusing on the solutions on the memory controller side. And there's another work that I would like to talk about that looks into better partitioning of tasks in DRAM and the memory controller, which is called self-managing DRAM. And in this work, we want to enable autonomous in DRAM maintenance operations. The key idea is to prevent the memory controller from accessing the DRAM regions that are under maintenance by rejecting row activation commands. And I will relate it to RowHammer in a second. So what we do is, this is the current interface between the memory controller and the DRAM chip. We have a command bus, we have a data bus, and the memory controller sends some requests, and DRAM responds with the data, or like it writes the sent data to the correct location and so on. So what we add is that we add another pin for DRAM to be able to say, can you stop for a minute? Don't send so many requests to me. This is useful because if you are doing some maintenance works, the memory controller keeps sending stuff, and basically DRAM device cannot do these operations on its own because it doesn't know like when it will receive another command from the memory controller, right? And if we add this, basically we can, as a DRAM device, we can do some operations on our own and say that memory controller, please just give me a second. And basically leveraging the ability to reject an activation, a maintenance operation can be implemented completely within a DRAM chip. And this enables a couple of different things. First, if we talk about DRAM refresh, we can have fixed rate and variable rate refreshes all operating within the DRAM chip. And in terms of RowHammer protection, basically we can implement these mitigations inside the DRAM device, and it can keep track of the aggressor rows, and it can decide which rows to refresh, and then it can also do the refresh on its own. And there's another case of memory scrubbing, which I will skip for now. And in summary, the three major DRAM maintenance operations are refresh, RowHammer protection, and memory scrubbing. And we observe that implementing new and efficient maintenance mechanisms often requires difficult to realize changes in various components in here, including the DRAM interface and the memory controller. And in this work, SMD, our goal is to first ease the process of enabling new DRAM maintenance operations in DRAM and enable more efficient in DRAM maintenance operations, including RowHammer mitigation. And we just described how it works. Okay. So if you are interested in that, you can take a look. And this is a talk from one of the authors of the paper. So now I talked about like a lot of solutions from our group, and these are not the only solutions or works on RowHammer in the last 4 years or so. And I want to present a sort of like a more complete picture of the works that are out there. And we had many works in major conferences, both in computer architecture and security. There were a lot of attacks. There were a lot of mitigations, looking at different approaches. There were like a lot of even sessions dedicated on RowHammer, like many works. Some of them we talked about and some of them we were not able to cover, but you can all find those that are from our group on our websites, and you can check our talks on them. Yes, I was not expecting that many slides myself. Yes, and next we will talk about some industry solutions. And we just checked like a lot of solutions from our side, from other researchers, from other groups. And industry also proposed a lot of solutions. One of them is called Panopticon. It proposes having per row counters in DRAM such that you can track all activations that are happening as accurate as possible. And it is a short paper that is also easy to read, and you can check the paper. It doesn't explain to a great extent what is the proposed mechanism, but it gives a good idea of what can be done on the device side. And this paper is from Microsoft and from another industry partner over there. And again, like Microsoft is not, based on our knowledge, is not a DRAM manufacturer, right? They don't do the device itself. And it is curious to see they're also looking at these problems and vulnerabilities and trying to cover them. And there's another paper from SK Hynix. This is one of the first papers from a DRAM manufacturer, again, looking into per row activation counters and implementing those in the device and exploring different approaches again. We have another paper from Samsung that is doing something similar. And lastly, we had actually a recent update in DDR5 standard in just like 2 months ago or something, 1 month ago. And it implements per row activation counters in DRAM and also creates this back-off signal, which is similar to what we talked in SMD, self-managing DRAM, to say that okay, I'm doing some refreshes now. I need to do some refreshes now. There's an attack or there's a row being hammered, and the memory controller issues a refresh when it receives the signal. So this is not, again, like a fully explained and detailed mitigation out there, but it describes a solution that can be implemented in the device itself. And there is a blog post on this. And yeah, you can check that blog post. It explains it very well, very understandable. And then it also references Professor Mutlu's lectures. So it's a nice thing over there. And so again, the question is, are we now RowHammer free in this year and beyond? We're not so sure. So this is a relatively new paper that shows DDR5 chips are still vulnerable to RowHammer, but we should also note that the last update was not probably covered with this. But before those, like again, like we heard some claims about being RowHammer free or mitigating RowHammer, and this paper shows that it is not exactly the case. So again, we need better RowHammer solutions, and this might mean that main memory needs intelligent controllers for reliability, security, safety, and scaling. And we might need to look at these approaches again and consider their trade-offs in designing these new, better solutions. So that slide starts concluding a bit. Should I go on, or do you want to conclude? Yes, if there are any questions, I'd be happy to answer. You might need to turn it on.
There is a regression attack. We can have like RowHammer effect. But I want to know there is a real case scenario, like when we are just reading DRAM, we have like the RowHammer effect.
So
if I understand very well, like if we read several times, then before we do refresh, we can have RowHammer. If we do refresh, we will have it.
Yes, so maybe I can repeat the question for those who didn't hear it. So maybe if the microphone works, you can also.
Okay, yes. I want to know if there is a real case scenario where just we are reading the DRAM and we make the RowHammer effect. Because I think RowHammer, like if we refresh, then it will not happen. But if a lot of reads happens before the refresh, then we will have the RowHammer. Like I think if we have a compiler and the compiler knows that we need this data a lot of times, then this data will be in the cache. So if we, but if maybe we have a lot of cores, like and all of them they want the data from the same row, maybe this can make a RowHammer or like
That's a valid scenario, and also if we have interference in the memory, the caches might not work as well as like we predicted, right? We would still have many activations to the same row within the refresh period, and as the RowHammer threshold decreases, that threshold, I mean, just let's say that it's around 1K. It is not like a super high number of activations when you consider the refresh interval. So benign applications could reach that point, and we measure like the activation counts of those applications, and we see that with low RowHammer thresholds, they again start to hammer, even though they don't, target creating an attack or something like that. And if we have like more cores that have accesses to same rows, that could be a scenario where you would observe a lot of row activations as well. Does that answer the question?
The second one, but the first one didn't understand very well. Maybe.
Okay, so to give like a definitive answer, benign applications can hammer as well, yes, from what we observe by measuring the number of activations that we see in these applications and considering the current and future DRAM chips with different RowHammer thresholds, yes.
Like an application can call, like, I don't know, 1,000 times the same row in a few time, like before fresh, something like this.
Yeah, yes.
Many more times, actually. Yeah, I would recommend, so there was actually RowHammer was first really found in the field because an application induced these errors. And some Intel engineer finally talked about that in the DRAM security workshop in last year.
Thank you.
There are applications that do not necessarily go through caches, right? You can have uncacheable data. And if you have uncacheable data that's requested by many processors at the same time, they may actually have hammering many activations that are.
If we consider the solution with dedicating basically a counter to every row, just a bit to ask, is that overhead really that significant? Because it's like dedicating a few bits of counter memory to a row of many more bits doesn't sound like such a huge overhead. It sounds like basically less than you would need to dedicate to, for example, an error correcting code. Is that really the memory the issue there, or are there other issues that prevent this approach?
So I would agree that it's not that, like significant when you think of all the cells that you already have. And it is not just I guess like changing the DRAM is sort of like one of the things that we need to consider, right? And before like these last updates and last papers, what we saw is that manufacturers were not interested in solving this in the DRAM device itself that much, so that they implement these in DRAM. And that's why we looked into putting these in the memory controller where we can design maybe more freely. And again, it seems again costly to us to put such a big structure in the memory controller side. And that's why we were focused on lowering that cost with inaccurate but still good solutions, right? Inaccurate tracking based good solutions. And with these new updates and papers, I guess we can say that it is a doable thing and people are interested in that, meaning that manufacturers are maybe interested in that. And that's something that we are very excited about.
Thank you.
Is that correct?
Yeah, basically.
Overheads may or may not be large, but is it good?
If it solves if it's all, the argument I understood mostly was that it consumes a large amount of counters, but I thought it's a relatively small price to pay to solve the issue. If it does solve the issue.
Yeah, that's the question basically. Does it really solve the issue? So I think in the end, the solution requires, well, there are multiple things. How do you update the counters? That's one thing. Because updating counters is not easy, right? And you need to know by how much you implement the counter based on a given activation, or how long you keep the row press.
Couldn't you place that counter? Basically, if you have to do it in a memory controller, it gets more complicated, but couldn't you place it at the level of like the row buffer? Basically, as long as the row buffer is activated, you increment it every clock cycle, for example.
Potentially, right? But that needs to be tested, right? And it needs to be figured out Like, what's the appropriate update mechanism?
Hmm?
None of this is described in any of these opaque papers. Basically, manufacturers are resorting to security by obscurity again. Like, none of this is described. So that's part of the problem, is how the update counts. The second problem is, when do you decide to take a mitigating action? Okay. At what threshold value? Like we discussed that it's very variable, right? And it depends on the temperature. It depends on all the testing that we discussed is very difficult to do. So you may pick a very large threshold value or a very small threshold value, and that directly impacts your performance, energy overheads, and the counter size also. And also it impacts whether you actually catch the misfits that happen in corner case conditions. And the third issue is, what is the mitigating action you take? When you take the mitigating action, what happens? Do you actually update the counters for something else? Like we discussed with the Google paper, right? If you refresh the adjacent rows, are you actually causing RowHammer for something else that's adjacent to that row that you refresh? So the problem is actually a little bit more hairy. And none of this is really discussed. Oh, we have these counters, and we update them somehow, and we mitigate the problem somehow. It's very obscure, basically. So the problem is much deeper. This could be, actually, when we wrote the paper in 2014, this was a solution we dismissed. We said that this is too costly. I think cost is actually now 10 years later, after developing a much more deeper understanding of the problem, cost is a smaller part of the issue. Question is whether or not the problem is solved. And I think that requires really answering these three questions at the very least. Does that answer your question?
Yes, thank you.
I want to sort of re-ask my last question because I'm sort of trying to convince myself that it is not possible. So I'm asking this because you said that the preventive refresh works, but takes a lot of bandwidth. And you also said that it's an assumption that you can't concurrently pre-charge all other lines and let the aggressor be read.
So regarding the preventive refresh versus and the bandwidth consumption, is just like focused on one approach of inaccurately tracking or introducing probability. And it's like pretty specialized to the existing works that are out there, that were out there. And what we observed that there is that they do these preventive actions based on these inaccurate measurements or like estimations of the activation counts. And that was what was consuming a lot of bandwidth. And also like some special cases for some works out there introduces more memory accesses that consume, again, a lot of bandwidth. So,
but how does it consume bandwidth if you do it concurrently?
It's not that you do it concurrently. Yes, maybe that was not clear. You don't do it concurrently. You get the activation count and you decide on refreshing, and then you send one by one to all victims some refresh commands. Not refresh commands, but activate precharges. And then that consumes, like that makes the DRAM unavailable for some time, right? Some of the requests are being delayed.
Right, so we could potentially pre-charge every other line except for the aggressor to a partial voltage level, not the entire swing, to prevent bit flips concurrently.
I'm not sure if that's possible, maybe.
What do you mean by pre-charge?
Yes.
But refresh also takes a lot of time, maybe, yeah.
Yeah, so whenever you refresh a row, it basically makes the whole bank unavailable. So, yeah. So while you're refreshing a row, the whole bank is unavailable, right? So you cannot access any other data in that bank. So it takes time as well. We are talking about like tens of nanoseconds for each refresh. And whenever an aggressor row reaches to a counter value, the threshold, you need to refresh multiple rows. So it adds up to like hundreds of nanoseconds. So it takes that time, and you cannot access the bank. So that's why you lose your bandwidth.
Okay.
I guess you're not convinced. Maybe we can take it offline in the coffee break.
Yeah.
Well, just when someone wants to implement this attack, they are relying a lot on flashing the cache, right, of the instruction, of this kind of instruction. So do you think it makes sense to also implement some mitigations on the CPU side, like limiting this kind of instructions or something like that? Because all these solutions are on the memory controller or on the memory itself. So I don't know what's your opinion about that.
We can certainly have some solutions based on the behavior, like detecting the attack based on the behavior of the cache, or maybe force some data to be cached in the closer levels, right? So that you filter some accesses. But this is again similar to, I mean, we don't discuss this, but like side channel attacks, right? It's like blocking the way to do one thing. If you let's say that restrict the usage of CL flush or like flushing the cache line instructions in any architecture, that just blocks one way to do it. And usually attackers are able to find other ways to do it anyways. They bypass caches with a lot of like evictions and so on. So you could still experience this because you are not fundamentally solving the issue that is in the memory device, right? You're just blocking some ways to do it. So yes, you could potentially have those solutions, and it would be possible to maybe filter some activations and prevent some attacks, but you could still have more attacks that are, you know, going through different routes such that they can get RowHammer bit flips. Any more questions? Yes, please.
Refresh period? Like, can we guess how many RowHammer attack can happen? I mean, how many rows can be attacked in one refresh period?
So we can calculate the number of activations that we can do in one refresh period, and then we can divide it by the RowHammer threshold to get the number of total like aggressor rows, possible aggressor rows. And we do those calculations in our works. I'm not like exactly sure about the numbers right now for any like RowHammer thresholds, but we do those calculations and we configure our like tables and everything based on that. So you can find those numbers in our papers.
Does it help like to make to find theoretically also what's the minimum number of counter that you can use if you have like no magic way to update them, but yeah, the minimum number of counter you can use in your solution?
Yeah, based on the number of possible aggressor rows, you can calculate it theoretically, and Misregre's algorithm does that. There are a couple of works, one of them being Graphene. I guess it's the first work that uses Misregre's algorithm. We have some references in the slides. Maybe you can check those. And also Count-Min-Sketch algorithm, again, gives you some, basically it does some calculations based on that, again, minimizing the number of counters that it implements. So yeah, there are some algorithms, and these works usually look into those. Yes, please.
So in a 64 millisecond refresh window, thank you. In a 64 millisecond refresh window, you can fit like around 1.3 million activations. And if you assume that only like 1,000 activations are enough to induce a bit flip, then you can do the math. Like more than 1,000 rows you can concurrently hammer. So it's quite a lot.
Thank you, Guy. Yes. Yes, please.
Okay, I was wondering if there were a software solution, like more commonly adopted software, because I guess it's easier also for the industry to change the software rather than this mature technology that is DRAM.
Yeah, there are some software solutions that I guess we sort of talk about in the slides as well. I'm not sure, like, so they are out there, but again, they're not fundamentally solving the issue. And basically, again, you could devise an attack that bypasses them, possibly, if they don't have a security proof. If they do, that's good. But when we consider software level solutions, they are usually not as effective, or maybe like they have higher performance overheads, or like other trade-offs are in the matter, like you need to think about other stuff as well. So we are mostly interested in looking into hardware solutions, because there you can see like which ROVs are being activated and so on. You have like a more maybe control over stuff. But I feel like you're going to add something, but you're just holding the microphone.
Yeah, just a quick thing. So if you're proposing a solution at software level, you need to go through a lot of abstraction layers, right? So you're working with virtual memory addresses, for example. You need to go through the address translation. You even don't know how the memory is mapped into DRAM in the memory controller, like which bank, which row you're going. So all these actually obfuscates a lot of information, basically, and it becomes really hard to observe precisely which row is activated when. And you don't have like necessary, sufficient amount of hardware performance counters, for example, to understand this. So that's the main problem. So there are many solutions in software level, especially proposed in like after 2015 until like 2020 or something like that. And pretty much every solution is followed by another attack that bypasses that solution.
Okay, thank you.
So the hardware itself can also generate like a significant amount of memory requests, including memory accesses. So that's something like completely transparent to software. Let's say, for example, the cache coherence protocol in multi-core, multi-processor environments. Some careful design in that part can just like cause a lot of activations. There's a paper called Moisi Prime that they demonstrate this can actually cause RowHammer bit flips, and you cannot defend against these cache coherence protocol-induced things in software. So, yeah.
So we've seen DDR4, DDR5, LPDDR mentioned. How about the GDDR memories that are used in graphics accelerators? I'm not familiar with how they're implemented, but are they also affected by RowHammer or similar attacks? And if yes, is it even a problem?
I'm going to say yes, but probably someone can answer it better than me.
Basically, all DRAM today internally is the same. What's different between all of these different types of DRAM is the interface. Oh, okay. Yeah, all DRAM today is internally the same. The array structure that we described, peripheral circuitry, is all the same. What's different is the interface, the voltage levels, the data rates, etc. So this is a problem. RowHammer, RowPress, there are problems with the internal arrays, which means that any DRAM that uses the same internal array and same technology is vulnerable. So that's why we see the same things in HBM. We don't talk about that, but GDDR is no different except for the interface.
Thank you.
Any more questions?
So you mentioned before the break that there can be 3 aggressors, consecutive aggressors, and 2 victims, one above and one below, right? So do you think that the solution of the counters also can be a solution for this? Because it's going to be much complicated, I guess, to do the counting.
I'm not sure like which example.
The one of Google, the example of Google.
Half double one.
Before
Okay.
the break.
Yes, I will try to show it. No, that didn't do the thing that I was aiming to do. The short answer is yes. You basically we need to account for the preventive refreshes and count them as activations as well. So in that case, we need to count those like preventive refreshes that are happening because of some other aggressor row as the activation counts, and you probably need to refresh based on those as well. But so behavior over there is a bit more complicated, and it could make the mitigation a bit hard to account for it, I guess.
Because I believe that to reset the counter, it's unless you refresh the two victim rows, right?
And then refreshing them probably affects the other one, right? Or
no, but
you're
just
not
once, I guess, so it's not a problem, right? But I was thinking, since you have 3, when do you reset the counters then?
So I'm not sure if that changes the solution that much. So over there, having many aggressor rows consecutive with each other, you would still, I think, count preventive refreshes one by one, and then I'm not exactly sure. I think it's the same, but maybe we can discuss offline if you have like a certain attack pattern in mind that would cause that mitigation to break.
Yeah, because I was just thinking if the one row can be an aggressor and victim at the same time. Just since there are 3 consecutive rows, so maybe the second row can be an aggressor at the same time. It can be a victim as well. Yeah. So just thinking.
Even refreshing your row can actually use it. So if you have a paper that takes it, yeah, so you need to account for that.
I don't have much things to say actually. Nisa already explained, I guess. Like basically, you need to count each one of those refreshes as well as like another activation, and you need to increment your activation count based on that. So you need to timely refresh your actual victim.
I'm almost there. Yes, that's the slide. I found it. Okay.
Maybe you guys should be doing research on RowHammer. You're asking very detailed questions, which is good. I'm not sure if the industry is asking this much detailed questions related to also these techniques.
There is one over there. Do you want?
So I think one asked the question like if we can do a software solution for RowHammer. Do you think that if we for critical applications, if we make like constraint on the compiler to take in consideration this effect of RowHammer, then we can actually reduce the effect of RowHammer just for the application, not when we have attack. It's like to reduce the accesses or the calls for the same row directly when we are compiling I mean, even before we load the code, something like this.
So the compiler can optimize the code such that it doesn't go to memory as much. So one way to do it is actually, I guess, like forcing to cache that data, and that might not work because maybe you have more interference that the compiler is not aware of, or basically you could find a way to bypass it again, even though the compiler optimizes well for it. I guess it's already optimizing very well for it, right? Because we don't want to go to memory because of the high latency anyways. And I'm not sure, like in terms of security implications of RowHammer, what could we do on the compiler side? Because I'm not like thinking of that angle that much, but these optimizations, they're not guaranteed to work to prevent RowHammer from my point of view. And basically they still need to rely on some mitigation mechanism in the memory controller or the device itself that considers how we fundamentally solve it. And again, yeah, we can have like some mitigations based on the compiler or software optimizations, but I believe that again, like we need to think about those like trade-offs of the stack, whole stack, and memory being not that easy to understand from that point of view, and so on.
To make the answer shorter, it's very difficult to imagine that the compiler does. What can the compiler do, right? You can limit this application, but if some other application is causing bit flips, you cannot do anything about that. Right? You can imagine solutions at the operating system level that could isolate things, but I think we already discussed that earlier. I don't think the compiler has any role to play here, unfortunately. But operating system could. But in general, the problem with those solutions, they're either not secure enough, or they cause a lot of overheads. I mean, one software solution is really integrity checking. So if you actually write your program, and you can actually compile it and do that potentially, right? You could keep checking whether something happened in your memory, right? If you can detect something changed in your memory without you changing it, this is not an easy way to program or and it's very costly also if you keep checking the integrity of your memory over time, right, without hardware support. That's a potential software solution, basically. Yeah, it's post-mortem. Basically, you would get data corruption, you would just detect it, right? And whether or not that's useful, it depends on when you detect it. It may be too late. Does that make sense? So if you really want to prevent the problem, as we have been arguing for, then I think software solutions are very tough. Yeah. Yeah, but we discussed it earlier, right? That's not enough, essentially. You can't use error detection codes, then you need to build a huge error detection. Yeah, you need to basically have a lot of storage overhead. Yeah.
The RowHammer mechanism for. So what happens if you employ the RowHammer mechanism for long enough that the second bit flips?
I couldn't catch the first part. Can you repeat again?
So I said that regarding error correction codes, are they really a solution? Because if you activate RowHammer for long enough, maybe a second bit would flip, so this will not really solve it.
It depends on the strength of your code, right?
Yes.
If your code can detect or correct 10 flips, 10-bit flips in a code word,
And if you never get more than 8-bit flips in a code word, then error correcting codes would solve the problem. The problem is the overhead of such codes. It's very high.
Yeah.
Yeah. Nobody implements that sort of code today in DRAM.
Thank you.
Yeah.
So,
Okay. Are you going to conclude? Go ahead.
yes, I'm taking this as you don't want to conclude it.
I mean, I can conclude if you want me to.
It's
Okay,
fine.
maybe I'll conclude.
Okay, then.
I mean, it's good that there was a lot of discussion over here, actually. Maybe I'll use this one since it takes more latency. I want to give some time for Konstantinos since he prepared stuff. What is the screen? I think that's fine. Let's see what's. Oh, okay, yeah. Maybe I want to give you some perspective. Yeah, I think it's fine. Yeah.
I think.
Okay, yeah.
I mean, I think we already covered some of these, so I don't want to cover more. But basically, I think we need to really understand these errors more. You've seen this already. Let me actually do some things over here. So you could argue that, again, why are we dealing with this? RowHammer, right? What's going on here? Okay. Essentially, it's fascinating. Right? So you can have other types of errors also that may be slipping into the field. So we do these large-scale studies and we find errors in the field. Why is this happening, right? RowHammer could be one reason, but are there other reasons? So it's always good to ask this question. And as I mentioned earlier, yesterday, this is all about robustness in the end. You may not care about security. You may say, okay, nobody attacks systems this way. Yes, maybe, although I wouldn't dismiss it. But it could be a safety problem in the field, right? I don't know if you see all of this, right? So you may also say, okay, this doesn't happen in some emerging technologies. I would suggest thinking again. This sort of read disturbance is actually quite prevalent in flash memory. We studied this a lot. In fact, one of the reasons why we did RowHammer studies in DRAM was because we knew a lot of the read disturbance errors were happening in flash memory. And you needed actually sophisticated mechanisms to prevent them in flash memory and SSDs. Existing SSD controllers actually have those sort of mechanisms. I'll mention a paper later on. Emerging technologies, actually, people have shown in simulation that this sort of errors happen in STT-MRAM and other emerging memory technologies also. So whenever you scale the memory technology to small node sizes, you will get bit flips. The nature of the bit flips may be slightly different, how you induce them. In fact, in flash memory, it's slightly different. In flash memory, actually, it's a bit very different. So whenever you want to access a page in flash memory, you apply very high voltage to all of the other pages in the same block in flash memory. So you're really disturbing not just one row in flash memory when you access one row, you're really disturbing all of the other 255 rows, or how many rows do you have? So the disturbance that you cause is actually a lot higher in flash memory, and this is a much bigger problem in flash memory. Now, the upside in flash memory is there are already intelligent memory controllers protecting it. So whenever you access an SSD, you have to go through a controller that does a lot of error correction and all of these optimizations to fix the errors. Okay, again, I don't want to take time because I want Tim to present a little bit, at least a little bit. I think we need a lot more understanding to do. Basically, even though we've understood a lot in this case of RowHammer, we still need to understand more. And there are other bit flips potentially. So we need a lot of modeling and prediction. I think real devices are actually very important. We need to architect carefully. This is, I think, where we're having difficulties in industry today. Basically, we're not having principled architectures that partition the duties between the memory and the controller and the software very well. Right now, we're back to square one. Remember, the story was, okay, RowHammer is reported. People don't talk about it. After some time, the manufacturers say, oh, we solved the problem. Everybody believes them. And then we write the trespass paper saying that, oh, you didn't actually solve the problem, right? Now we're back to square one. In 2024, people come up with per row activation counters. Oh, we solved the problem. They're more careful about that. We believe we solved the problem. At least they say we believe earlier. Before they didn't say we believe. We solved the problem. Forget about it. Well, did you really solve the problem, basically? And I don't believe the problem is solved because of the reasons that we discussed, right? You really need to rigorously answer the 3 questions that we discussed earlier to show that you solved the problem. Basically, there's no security proof at this point. So I think we really need to think about how we architect our systems. And all of these are true over here. We cannot give up performance and efficiency. And I believe you really need patchability in the field. So if you have a memory controller that's much more programmable and intelligent, over time, if you discover some of the issues in the field, you basically update your memory controller. And your memory controller can actually fix some of these issues in the field, right? So that's the solution direction that we've been arguing for a while. And I think that's becoming even more important. And design and test, I talked about online profiling, for example. That's going to be even more important going into the future. For example, if there's an aging effect in RowHammer, so in one of Girai's papers this year, he showed that if you hammer DRAM continuously 68 days, ask him why it's 68 days, the threshold, you mean the number of activations to induce RowHammer reduces by about 5% or so in some cases. Now, this means that if you set your threshold based on some number, that threshold should reduce by 5%, right? So aging has an effect on these thresholds, and we don't understand that at this point. Unfortunately, there's no study that shows that. GI study is basically one example of aging, right? So this sort of aging effects can be handled through online profiling with intelligent controllers, I think, going forward. That's why we keep building this infrastructure. And this is the flash infrastructure that I mentioned. Actually, we built this infrastructure before we built our DRAM infrastructure, and we tested read disturbance issues in flash. And if you're interested in that stuff, oh, I guess you should read some of these papers. That paper over here. I don't know what's wrong with your screen over here. Normally when I present, I don't need to deal with all of this stuff. It's better to present with so redundancy is always good, as you can see. It's better if you present through Zoom on a separate computer, because this computer has a lot of other stuff in it, including the camera, I guess. Okay, but if you're interested in Flash, there are a lot of interesting works over there. Okay, now let me quickly give you my final thoughts. Actually, I mean, bit flips are interesting. In fact, as I said, read disturbance happens in many memories. It's not new. Bit flips are not new. The effect of bit flips on security is also not new, meaning there are some very intelligent security people that actually knew that bit flips were bad. And we know bit flips are bad because you should not have bit flips, right, that are exposed to the user. But security people knew about that also. In fact, there are early papers in 1990s that show that your cryptographic algorithms can be broken if you get bit flips. This is called fault attacks in 1990s, right? But I'll mention another paper. This is a paper that was published in 2003, IEEE Security and Privacy, a major security conference. And what these folks did was they basically induced memory errors in a real machine, and they basically showed that you could take over a virtual machine. This is very similar to the attack Google developed in Project Zero using RowHammer to not take over the kernel, that's a new attack, but to actually take over the Google native client, which is essentially a virtual machine sandbox, right? So the way they induce these bit flips, can anyone guess how did they induce these bit flips without reading that stuff? Hopefully you cannot read. Maybe your eyes are better than mine. Anybody? How would you induce bit flips in a machine? If you didn't know about RowHammer, and we were talking about 2003 over here, in memory, in main memory, DRAM. Yes? That's a good start. So you would go and radiate people's computers. That's one way. Well, that's close enough. Basically, you have physical access. Basically, you need physical access, and these folks actually use that lamp and put it next to the memory, and they got a lot of bit flips. And they basically showed that they could launch a probabilistic attack to take over a machine. This is a beautiful paper. You should take a look at it. And Google's paper, the blog post, partially is covered by this paper, I would say. So what RowHammer did is basically replace that lamp by loads and stores. And it became much more precise because you could induce bit flips in any location that you think may be vulnerable to RowHammer as opposed to many locations. Because if you take a lamp and put it next to your memory over here, you'll get lots of bit flips. It's a very low probability attack. But the fact that they were actually envisioned this attack in 2003, I think is fascinating. So if you think about that, people knew about these attacks, but this was not taken that seriously, right? Why? It required physical access to your computer. It required a lot of stars to align to work, basically. But with RowHammer, those stars align much more easily because now you can induce these attacks using software. And as a result, security folks did a lot of work building on RowHammer. So these bit flips are real to security folks right now. They can induce them. And this is also the disconnect between, I guess, the higher level security community and the lower level hardware community. If something cannot be done easily by software, security folks are not as worried about it. Makes sense, right? There's physical security also, but that's a smaller part of the security community. Okay, so I'm going to skip these. I'm not going to talk about that since we don't have time. But I think maybe most importantly, RowHammer really enabled a shift of mindset in mainstream security researchers. And when you talk to security researchers, they will say this. General purpose hardware is really fallible in a widespread manner. And this mindset actually enabled many system security researchers to examine hardware in more depth. That's why hardware security is actually a fascinating topic. You'll see lots of hardware security papers today in major security conferences. Whereas in the past, this was actually a very small minority. So when I actually wrote my first paper when I was at Microsoft Research, we published it at Unix Security. It was a memory performance attacks paper that I mentioned. And this was the only one of the 2 hardware security papers. I was in a session titled low level. So somebody else presented a low level paper and I told basically them, I'm going to present an even lower level paper. So now actually there are a lot of papers, there are sessions titled RowHammer in hardware security conferences. So people actually who worked on RowHammer tried to understand hardware more. And I don't believe it's a coincidence that 2 of the groups that discovered Meltdown and Spectre. How many people know about Meltdown and Spectre here? Okay, some people maybe. These are basically side channel vulnerabilities in major processors due to out of order execution, caching, speculation, all of them combined, let's say. Essentially those folks worked on RowHammer before and they got fascinated by other issues that may be lurking in hardware. So I think there's a lot more to come in this area, not just in bit flips, but also hardware. And today people are actually seeing that processors are also seeing these bit flips. You may have seen papers from Google and Facebook. They basically say in our data centers, we run these processors and sometimes we get silent data corruption in logic, not memory. And they made a big deal out of that saying that, oh, we have a lot of problems with silent data corruption. Okay. Okay, I think I've already said everything over here, maybe. The bad news is all of these things will get worse, both in memory and logic. The good news is I think hopefully we're smarter, although we should be more, even more smarter, I think. I think at least in research, we're fully aware hardware is easily fallible and people are developing both attacks and defenses. I think we should be developing even more principled models, methodologies, and solutions going into the future. With that, I've exhausted your slides now. I'm not going to take questions because I want Konstantinos to cover what he's interested in covering. He's doing a lot of exciting work in a totally different area. But feel free to ask questions later on during dinner or at some other places. And hopefully you'll use redundancy, another computer maybe. Or if it's uploaded over there, it's fine.
Can you hear me well? Yes. Thanks, everyone. I will be the one who will discuss about virtual memory today, which is a fundamentally different, I would say, concept compared to RowHammer, which is a reliability-based problem. I'm Konstantinos. Some of you might know me from the Mixer leader groups. So I'm jumping into my 4th year of PhD, and I'm basically working a lot on these hardware OS software co-design topics. In today's lecture, I'm going to cover 2 works, or let's say I'm going to try to cover 2 works. One is called Victima, which was presented in Micro 2023. We demonstrated how one can basically make
much better use of the cache hierarchy in order to accelerate address translation in modern processors. And the second one is Utopia. In Utopia, we demonstrate that the page table design has lots of drawbacks, and we find out an alternative way with which we can perform address translation and accelerate the process. So I'm jumping to Utopia first. The title of the work is Fast and Efficient Address Translation via Hybrid, Restrictive, and Flexible Virtual to Physical Address Mappings. And this is a collaborative work by Safari at ETH Zurich and other universities. Let's see the executive summary first. So we know that the conventional virtual memory frameworks enable a virtual address to map to any potential physical address. So this sort of flexibility that the current system is introducing, it has basically two big disadvantages. One, it causes high translation latency. And the reason we have this high translation latency is because we have really big page tables, we have irregular memory accesses in modern workloads, and this is a lethal combination. Second, this expensive access to the page table also lead to large translation-induced interference in the memory hierarchy. What does that mean? This means that whenever we load the page table, we essentially create contention in the structures that are shared in the current multi-core systems. So what is the motivation behind this work? So we want to restrict the address mapping, so this flexible address mapping, and this will lead to a more compact translation structures, and this way we will reduce the overheads of address translation. However, there is a problem. If we restrict the mapping throughout the whole memory, then we might limit the core functionalities of virtual memory, one of the most important ones being data sharing. Second, we might increase swapping activity, and why this would happen? Some virtual addresses might not map at all inside the physical address space because of this issue. So what is our key idea? The key idea is to get basically the best of all the worlds. Utopia is a new hybrid virtual to physical address mapping that allows both a flexible and a restrictive hash-based address mapping to harmoniously coexist in the system. And how does this happen? We use different physical memory segments. One, we have the restrictive segment. So we have a virtual page here. And how do we map this virtual page to the physical space? We pass it through a hash function. And through the hash function, it points to a single physical address page. It cannot basically point to any other page in the restrictive segment. In this scenario, for example, we use the modulo hashing to place the virtual page inside the physical address space. What does this offer? Fast translation. We simply hashed, we code back the physical address. What's the problem? We have limited virtual memory features. Can we do sharing? Can we do efficient protection this way? The second segment, it's the flexible segment. It's a conventional original virtual memory segment. What does that mean? It uses a page table that decides the mapping between the virtual page and the physical page. The page table stores all the information about all the pages for its process. For example, in x86, use a radix-based page table to perform this operation. What does this lead to? Slow translation, and I will show you concrete results later. However, we support all virtual memory features. And why is that? Because the current page table design that allows a virtual page to map to any physical page gives us really high flexibility. In Utopia, we demonstrate that it outperforms the state-of-the-art contiguity-aware, really fast offset-based translation scheme by 13%. And we also achieve 95% of the performance of an ideal perfect DLB, where we basically completely ignore and we avoid address translation. The code is open source, and you can find it uploaded on GitHub. That's the outline for my talk, and we go directly into the background. Some basics. Virtual memory is one of the cornerstones of most modern computing systems, and conventional virtual memory designs provide application transparent memory management, data sharing, and process isolation. And one of the core features of the virtual memory management is that the mapping between the virtual to physical pages is fully associative. What does that mean? On the left, we have the virtual address space, and on the right, we have the physical address space. When we have a virtual page, it can map to any possible page in the physical address space. And how do we keep track to which it maps? Using the page table. So the page table is simply a dictionary that tells us to which physical page a virtual page maps to. So we need to perform a page table walk, which is looking up the page table to find out the desired mapping. How does the page table walk process look in x86-64 systems? We split the virtual address into 36 bits, avoiding, like, we compact it and we shift it and we remove the offset. We probe the first level of the page table. We find a pointer to the next level, and we do this operation recursively until we reach the last level of the page table, which is the fourth level. When we reach the fourth level, we find out and discover the physical frame number. And using this physical frame number, we form the physical address. But how many accesses did we need to achieve this? 1, 2, 3, 4. 1 for each level of the page table. In modern systems, we're even going to 5-level page tables because of the large increase in the memory capacity. The conclusion, we need 4 sequential memory accesses during a page table walk in x86 systems, 64 systems. So, but we need architectural support to perform this operation much faster. We won't walk the page table every time. So if we want to send a memory request to the hierarchy, of course, we need to translate the virtual address to the physical one. And resolving this address translation requires accessing the page table. However, as I said, this is a bit dumb. You don't want to access the page table every time you do address translation. So we will throw there a hardware unit, the memory management unit, that basically accelerates the address translation step. So what is the flow of address translation? We have our core on the left. We wrote our program in C. It produces some virtual address, and we have the memory management unit. So what is the memory management unit? It's the unit in the core that handles address translation. The memory management unit, eventually at some point, it would load the page table, it would read the page table, and decide what is the virtual to physical mapping. So in the system, there is inside the memory management unit, there is a 2-level TLB hierarchy. What is that? It's 2 hardware SRAM-based structures, some cases CAM-based structures as well, that store recent page table entries. It stores directly the virtual to physical translation. Whenever we miss in the L1 level, in the first level, we probe the second level of the TLB. And when we miss in the L2 TLB, then what would happen? We would need to walk the page table. And we have a circuitry for that. We have a specific state machine that basically generates the request for the page table and walks the page table. However, do we need to walk all the pages? Do we need to access all the pages from the memory? The answer is no. There is an additional page walk cache structure, again an SRAM-based structure, where we store the intermediate page table levels. We might store the second level. We might store the first level. Modern processors have 3 page walk caches. And this way, we do not need to load every time our page table from the cache hierarchy and the memory. So we receive the page table entry. And we find out the physical page number, some access control metadata, and we find out it's in the cache, it's in the DRAM and the cache hierarchy. Perfect. We send the physical address to the cache hierarchy, and we will retrieve back our data. The second and more weird scenario, more disturbing scenario, is that we receive the page table entry, but the entry is not in the DRAM. It's in the swap space, and the metadata and the page number told us so. So right now, the physical address space is split between the swap space and the DRAM. So how do we resolve the situation with a page fault? We stop execution, the OS gets triggered, it swaps in the page from the swap inside the DRAM, and then we continue execution using the newly allocated physical page inside the DRAM. Finally, how does the translation latency look end-to-end? In the best case scenario, we have a TLB hit. We easily retrieve the address translation from the memory management unit. What's the bad scenario, though? We do not have a TLB hit, and we need to load the page table from the main memory. This is a TLB miss. So we need to access either the caches or the DRAM to retrieve the page table. And as I will show you later, this costs a lot in terms of performance. Finally, we simply retrieve the physical address and we access the memory hierarchy. About address translation overhead. So we have multiple applications nowadays, generative AI, graph analytics with regular memory accesses, bioinformatics workloads, which experience really high address translation overheads. Why? Because they have high latency page table walks. This process that I described now is really expensive in terms of cycles. And second, these page table looks are really frequent. We miss a lot in the L2TLB structure. So in this plot, I demonstrate in the y-axis the page table walk latency in cycles for two schemes. One baseline scheme that uses the 4-level radix page table, and a scheme that uses the state-of-the-art page table that exists in the academic setup. Even the best performing state-of-the-art hash-based page table takes 86 cycles to access on average in these really data-intensive and memory-intensive workloads. Why? Because in this plot, I demonstrate in the y-axis the L2TLB MPKI, how many misses per kilo instructions we experience at the L2TLB. And we demonstrate this number across different and increasing number of entries in the L2TLB, from 1.5K entries up to 64K entries. Imagine this is a really big leap. And even the largest 64K entry L2TLB experiences 24 misses per kilo instructions. This translates to 24 page table walks per 1,000 instructions, which causes really high overheads in performance and bottlenecks. So where does the address translation overhead come from? High latency page table walks and frequent page table walks. And together, this leads to high performance overheads and high interference in the memory hierarchy. In this plot, we demonstrate the speed up of the state-of-the-art page table and of a scheme that uses a perfect TLB, no address translation overhead, compared to the baseline system. And as you can see, completely avoiding address translation can lead to an average of 31% higher performance, which is a really big and good headroom to work with. Second, interference in the main memory. As I told you before, there is translation-induced interference. And in this plot, I demonstrate in the y-axis the DRAM row buffer conflicts. How many times do I need to activate a new row in the DRAM? And there was previously another row activated for the state-of-the-art page table, and again a scheme that uses a perfect TLB. There are no accesses in the DRAM that happen because of page table accesses. So if we completely avoid address translation in this case, this leads to 30% fewer DRAM row buffer conflicts, which can show that if we somehow ameliorate this process, we can even reduce the contention in the shared resources, which is not expected as a first level optimization. So what is the idea? Restricting the virtual address to physical address mapping. There are previous works which have also shown some forms of restriction of the virtual address to physical address mapping, and they have shown that this way you can perform really fast address translation. How do you do this? We have this virtual address space, we have this page, and we do not use a page table anymore, we use a hash function. In this case, we use a hash mask, really simple. And after masking the virtual address, we find out that in the physical address space, our virtual address, virtual page, can only go to this one. What is the drawback of this scheme? If we employ a restrictive address across the entire memory, first we limit the core virtual memory functionalities, and second, as I said before, we increase the swapping activity. Why do we increase swapping activity? We might have 3 pages, but our virtual address might not be able to map to the 3 pages. It might map to an already allocated page. In this plot, I demonstrate on the y-axis the normalized accesses we do to the swap space, swaps in, swaps out. And I demonstrate the baseline system that uses only in restrictive mapping, and how does this work compared to a system that uses a fully flexible mapping. But the sole use of this restrictive mapping leads to a 2.37x higher swapping activity over the baseline. Higher swapping activity translates to more disk accesses and data movement between the disk and the DRAM, which causes really high performance overheads. So what is our goal in this work? We need to design a virtual to physical address mapping that provides fast and efficient translation using a restrictive hash-based address mapping, while at the same time it enjoys the benefits of the conventional fully flexible address mapping. So the key idea is Utopia, a new virtual to physical mapping that enables both a restrictive mapping and a flexible mapping, and they harmoniously coexist in the system. Utopia manages the physical memory using 2 types of physical memory segments, restrictive segments and flexible segments. So let's see how this works. In restrictive segments, we see here an example of a restrictive segment that has 4 pages. So when we translate, we take the virtual address, we pass it through a hash function, we find out the location of the page inside the restrictive segment. And this virtual page cannot map to any other position inside the restrictive segment. Fast address translation, but limited virtual memory functionalities. Second, we have a flexible segment. This is a conventional segment. A virtual page number, we use the page table, we can map it anywhere we want. This supports all the conventional virtual memory features at the cost of a high latency of address translation, which, as I showed before, it can be a performance bottleneck and also content resources with other applications. Let's see the properties of the restrictive segment, the structural ones, and how we perform address translation, efficient address translation for the data that reside in the restrictive segment. Structural properties first. Restrictive segment is organized in a similar way to hardware caches operate. You have seen set associative caches. This is how the restrictive segment works and operates. For example, we have a two-way associative restrictive segment with 2 sets. So it has 2 sets, and each set has 2 ways. And this set associative design offers high flexibility. We might be able to place our page in 2 different ways, not just in one, which, as I will show you later in the results, it reduces the number of collisions we have. We can have multiple restrictive segments in the system, and the question is, why do we need multiple restrictive segments? We can have 1 and 1. But for example, modern systems use both 4 kilobyte pages and 2 megabyte pages. So why not have 1 for each one of these? And this way we can have backwards compatibility with large page mechanisms. Existing Linux large pages provides both 4 kilobytes and 2 megabyte pages. You can place some of them to the 4 kilobyte restrictive segment for fast translation and some of them to the 2 megabyte restrictive segment. Second, how we do address translation for data in restrictive segment. We take our virtual page, and what is the process with which we can understand where is our data? We have 2 operations, tag matching, similar to hardware caches, and set filtering. So in tag matching, we need to compare the tags of all the ways with the tag over the virtual page. And we need a new array called the tag array that stores all the tags for each entry in the restrictive segment. So we take the virtual address, we pass it through the hash function, and we find the corresponding set index number and the tag for this specific restrictive segment. So for example, if the index is 1 and we search through the first 2 ways, we find out that we have a tag match because the first way and the first set is occupied by tag, which is our tag. The question is, do we always need to do tag matching? The answer is no. So we have a new data structure, a new process called set filtering, where we quickly discover if a set inside the restrictive segment is empty or not. And we can, this way, filter the tag mismatches. So the set filter is an array of counters that keep track of the number of pages in each set. And an example here is that we take the virtual address, we hash it again, we find the set number, and we probe this data structure. And this data structure tells us the following. In set 0, there is at least 1 page allocated. In set 1, there is no page allocated. So if we probe and we find out that our page is in set 0, then we will go and perform the tag matching. So this is the only scenario we will perform the tag matching. Address translation end-to-end. We perform an L1 TLB miss. We cannot avoid that. And then we do 2 operations in parallel. We walk, which means we perform tag matching for the restrictive segments. And we also perform the L2 TLB access in parallel to this tag matching operation so that we don't have performance issues. If we do not find our data in the L2 TLB and the data is not in a restrictive segment, then we walk the normal page table to find out our data that resides in the flexible segment. Some key challenges in Utopia. Which data should be placed in the restrictive segments? How we can maintain restrictive segments in the system along with the flexible segments, and how we can integrate Utopia in the address translation pipeline. First, which data should be placed in the restrictive segments? So the goal is to place the most costly to translate pages into a restrictive segment. And we propose 2 techniques to achieve that. One that works on every page fault, and one that works on that works continuously and tracks the cost of page table walks. The page fault-based allocation policy. So when the OS wants to attempt to allocate a page in the physical address space, it tries to directly place it inside the restrictive segments. So on a page fault, we measure the occupancy of the restrictive segment. Is it 90% occupied? Then we can place our page inside. If it's not, and we have a 100% occupancy in the restrictive segment, for example, we place it normally in a flexible segment because we don't want to pay for the overhead of evicting a page from the restrictive segment. However, if we follow this approach and we have high occupancy always, we will never place costly to translate pages inside the restrictive segment. That's why we have the page table walk tracking migration policy. In this policy, we use the unused bits of its page table entry as a counter that keeps track basically of two metrics: the number of page table walks and the cost of page table walks, which constitute the cost of address translation for this specific page. Each page table entry before had a physical frame number, some access control metadata, and now we use the unused bits to implement this sort of counter. Whenever this counter exceeds a threshold, which is always updated after each page table walk, we will migrate the page from the flexible segment inside the restrictive segment without taking into account the occupancy, which means that we will evict a page from the restrictive segment if the page is not free. How we can maintain restrictive segments in the system? OS supports Utopia in three ways: by handling the allocations inside the segment, replacements in a segment, how we evict data, and migrations to and from a restrictive segment. How we do allocation? We take the virtual page number, we instruct the OS, I want you to allocate this virtual page. It passes it through the hash function of the restrictive segment, and then it has access to a global tag array. What is this? It keeps track of all the pages inside its resseg for all the processes. And the global tag array gives us an answer. Okay, there is a free way in the set. You can store your data there, and we are good to go. The second scenario, no way is free in the set, same way as hardware caches. What would happen in this scenario in hardware caches? We would evict a cache line. What do we do now? In this scenario, we evict a page. How do we evict a page though? So we have a DMA engine which is responsible for migrating data between the restrictive segments and the flexible segments. So whenever there's a migration happening, we trigger the DMA engine that copies the data from the flexible segment to the restrictive segment without involving the host CPU. And this DMA engine exists in all modern computers, basically. Third, how we can integrate Utopia in the address translation pipeline. We have a new restrictive segment walker that enables address translation for pages reside in the restrictive segment. We have a specialized hardware circuitry that performs tag matching and set filtering. And this way we avoid expensive software-based access to translation structures. We do not need to invoke the OS every time we need to perform address translation for a page that resides in a restrictive segment. Second, we have two small cache structures for the tag array and the set filter. So this way, we can leverage any temporal and spatial locality for accesses to those two arrays. And last, we perform some minor modifications in the translation pipeline in the microarchitecture so that we can perform in parallel the restrictive segment walk and the L2TLB access based on the pipeline that I showed you before. So how does that look? We have a restrictive segment walker. It has an FSM first. What does the FSM do? It takes the virtual address and generates the tag array and the set filter addresses based on this virtual address. Second, it accesses these two caches, the tar cache and the SF cache, which store the recent tar and SF entries, software entries. Where do these reside? In the main memory, same way as the page table. So if we miss in the tar cache or the SF cache, we go and access normally the tar cache and the SF, the tar array or the SF array from the memory hierarchy. How does the end-to-end operation look like? Okay, let's discuss about the scenario we had an L2 TLB miss, and we perform in parallel two operations: the restrictive segment walk, which I just described, and the L2 TLB access. If the L2 TLB access misses, then it needs to wait before the result of the restrictive segment walk is determined. And then it will start another walk for the flexible segment to figure out if the data is in the flexible segment. This is a performance decision so that you can base it, so this is an energy or versus performance trade-off so that we can know, so that we do not perform the flexible segment walk every time we have an L2 TLB miss. First scenario, the page resides inside the restrictive segment. So the physical memory is organized as this. Our page is here in the restrictive segment. How does address translation happen? An L1 TLB miss, two parallel operations, which means an L2 unified TLB access, and the restrictive segment walk. And in this case, we have a miss in the L2 TLB, which means we need to stall on that front of the pipeline. But the restrictive segment walker tells us, okay, your data is inside the restrictive segment. So we do not need to perform the flexible segment walk. We can abort it. Second scenario, the page resides inside the flexible segment. Physical memory looks like this. Our page is here. Again, we have an L2 TLB miss. We trigger the restrictive segment walker. We access in parallel the L2 TLB. But what changes in this scenario? We stall. We wait for the result, but data is not in the restrictive segment, which means that we will start the flexible segment walk. Third scenario, and the most simple scenario of all, we have a TLB hits. So it doesn't matter basically where our page resides in, because if we have an L1 TLB access and we hit, we simply resolve address translation. And the second scenario, if we have an L2 TLB hit, again we resolve address translation and we abort the restrictive segment walk that was initiated during the L1 TLB miss. We evaluated the area and power overhead of our design using MacPath, a famous tool, and we compared to a high-end Raptor Lake, and we demonstrated Utopia incurs 0.64% area and 0.72% power overhead per core, because the memory management unit in modern systems exists per core. Our evaluation methodology, we used a Sniper multi-core simulator, and we extended it with multiple features of the virtual memory subsystem. And we also have a poster in Micro 2023 in the student research competition where we introduced a new simulation infrastructure that we created. It's called Virtuoso, and it's already uploaded on the GitHub, and basically an update is coming on Friday. We used many workloads from many different benchmark suites, irregular memory accesses, genomics, the recommendation engine provided by Meta. And the evaluated mechanisms are the following. We have a baseline system, a radix page table, and we have transparent huge pages enabled. Both 4 kilobyte and 2 megabyte pages are in the system, in the baseline system. Second, we have a state-of-the-art, large software managed TLB, which acts as a backup to the L2 TLB. Whenever we miss in the L2 TLB, we go and access a software managed, really large L3 TLB. State-of-the-art has base page table that delivers better performance than the radix base page table. Fourth, contiguity-aware address translation, where we perform really fast offset-based address translation. And then Utopia, using a 512 megabyte restrictive segments, one for 4 kilobyte pages, one for 2 megabyte pages, and a perfect TLB mechanism that always hits in the L1 TLB. Our performance results, this is the speed up of all the mechanisms compared to the baseline system, and we perform the second best performing scheme by 13% and the baseline radix scheme by 24%. And we reach the performance of perfect TLB by 95%. How does address translation look like? We reduce Utopia reduces the address translation latency by 63% over the baseline radix scheme, and 14% by the second best performing scheme called redundant memory mappings. How do we reduce the main memory interference? In the y-axis, we show the normalized DRAM row buffer conflicts, and we demonstrate that Utopia reduces the row buffer conflicts by 20%, 9% less than the perfect TLB. We're really close to the perfect TLB. We have more results and details in the paper, sensitivity across different hash functions, different restrictive segment sizes, the reuse level distribution of pages inside the restrictive segment, and much more. And you can find always the paper uploaded on archive, and we provide constant updates on archive. The paper remains alive, it doesn't die because of a conference. What's the conclusion? We propose Utopia, a new virtual to physical mapping scheme that enables both restrictive mapping and flexible mapping to harmoniously coexist in the system. And Utopia achieves 13% higher performance than the state-of-the-art contiguity-aware translation scheme and 95% performance of an ideal perfect TLB scheme. Utopia is open source, you can find it on GitHub, and in general we have a big simulation framework that we're constantly developing with respect to generating and evaluating such ideas. Thanks a lot. You can find again the paper. This is the GitHub link and the archive link. And I guess we don't have more time. Okay.
Much people want to skip dinner.
No, I will not sacrifice their dinner. Any questions though?
Are there burning questions? No? Okay, maybe you'll have a chance to ask questions to Konstantinos over dinner or tomorrow. Okay.
Cool.
You don't know where.
Okay.
So the dinner is gonna be